This is session B4, Bohr Model of the Hydrogen Atom, 1913. Last session we did the Rutherford model of the atom. He produced his model in 1911, saying that all of the positive charge of an atom and almost all of the mass of the atom are located in a very small, very dense nucleus. And his grad students, Geiger and Marsden, proved all the aspects of his model in 1913. Today we'll do the Bohr model of the hydrogen atom from 1913. The Rutherford model said that there was a nucleus, but did not say, what about the electrons? And physicists knew there was a problem with having a central nucleus and having electrons around it. The Bohr model addresses that. Now, this is not going to be a video like the normal videos we've done. I actually want you to read a paper that I created for you. It's at this URL. The URL will be on the YouTube page as well. It's 14 pages. I think it'll take an hour or maybe longer. If it's parts of it may be too much more physics than you want or know, you can skip past those. There'll still be a lot of value in the paper if you read the paper. So I'm hesitant to give you a synopsis of the paper because I don't want people to just use the synopsis and skip the paper. On the other hand, some people need the synopsis in order to be motivated to read the paper. So here's a synopsis. Bohr produced a model whereby the single negatively charged electron in a hydrogen atom can be in specific circular orbits around the positively charged nucleus, the proton. He gave the radiuses, the radii of those orbits. They're always a multiple of the length called the Bohr radius, A0, which is about half an angstroms. But the multiples are the Bohr radius times an integer squared, where the integer n goes from 1, 2, 3 on forever. For a particular number n, quantum number n, there is a specific radius and a specific bound energy, E sub n. That energy is minus 13.6 electron volts divided by n squared. So for larger n, the magnitude of the bound energy gets smaller. It's always a negative quantity, it's a bound energy. Bohr also found that for each quantum number n, the orbit would have a specific orbital angular momentum, and that the orbital angular momentum was quantized in units of h bar. So the angular momentum is n times h bar. Now, not in his paper, but in my paper, I discuss and show that the Bohr model is consistent with the 1924 de Broglie relation, and it is consistent with the Heisenberg Uncertainty Principle of 1927. So the Bohr model says there are circular orbits. He knew, and physicists of his time knew, that was impossible. But the success in the Bohr model predicting the size of a hydrogen atom, and they knew approximately what that size needed to be, and the bound energy levels, which they could compare against the Balmer series of emitted light, emission spectrum. Bohr's model was sufficiently successful that it showed that they needed a new physics beyond classical physics. They needed what will later become called quantum mechanics, and published in 1925. And then when we have real quantum mechanics, the solution for hydrogen will not have the electron in an orbit. However, Bohr's model led the way to there being quantum mechanics. So there are a lot of reasons why you should read the paper. There's a lot of interesting information in it, and I strongly recommend that you read the paper. If you have access to the paper, I recommend that you read the paper. The remainder of this video is me reading the paper aloud for anyone who is visually impaired. But read the paper if you can. So this paper is a paper that I wrote, the Bohr model of the hydrogen atom. This is a derivation of the Bohr model of the hydrogen atom, as you could find in any introductory quantum mechanics book, but extended to other hydrogen-like ions with a single electron, highlighting the importance of the quantization of orbital angular momentum of the electron's orbit of the nucleus. It's not really an orbit. Showing the significance of the fine structure constant, using an SI-MKS derivation instead of CGS electrostatic units for ease of calculating the ground state energy in electron volts and the Bohr radius, which remain important today, 100 years after Bohr's work. Checking the results against the subsequent Heisenberg Uncertainty Principle and the de Broglie relation, neither of which was known at the time of Bohr's publication, and stressing that with subsequent correct quantum mechanics, the Schrödinger equation, the electron is not orbiting the nucleus in fixed orbits, and we should not think in terms of orbits or trajectories, but rather appreciate the Bohr model for showing the definite need for new physics beyond classical physics, the need for a correct quantum mechanics. If you spend the hour or two it takes to go through this paper, you'll have a good understanding and all you could ever wish to know about the Bohr model, where it's correct, where it's incorrect, and how it motivated the need for quantum mechanics. You may encounter physics with which you're not familiar, but continue reading to the end. Skip over bits that are not familiar, or use Khan Academy to learn more. In 1911, Rutherford explained the 1908 to 1910 experimental results of his graduate students Geiger and Marsden, whereby high-energy alpha particles, known to be positively charged helium nuclei, from radon or radium, hit a very thin gold foil, gold is extremely ductile, and were sometimes deflected by a high angle, including backwards. Rutherford proposed that the positive charge in the atom was not a continuous, distributed pudding or cloud or soup, but a concentrated, small, dense, heavy nucleus with almost all the mass of the atom, much heavier than electrons. In 1913, Geiger and Marsden produced new experimental results that confirmed Rutherford's model of the atom. J.J. Thomson's plum pudding model was now dead, but Rutherford's model did not explain the electrons in the atom. Danish physicist Niels Bohr realized, as did Thomson, Rutherford, and other physicists, that classical mechanics and classical electromagnetism could not explain any stable configuration of finite size between a small positively charged massive nucleus and a negatively charged low-mass electron. An accelerating electrical charge classically would radiate energy, lose energy and quickly in 16 picoseconds, 16 trillionths of a second. The particles would collapse together into a single point with no size. And yet atoms were known to have finite size on the order of angstroms, 10 to the minus 10th of a meter. Why don't atoms collapse? Bohr realized that the path forward must be to develop a physically incorrect, or at least incomplete, model of a lightweight, mobile, negatively charged electron point particle in stable orbit around a heavy, essentially immobile, positively charged hydrogen nucleus point particle, and that a valid model must correctly predict energy levels whose difference between the energy levels matched Einstein's photon energy formula, E equals hc over lambda, for the known Balmer series of visible light hydrogen emission lines, the Wikipedia page Balmer series, without introducing multiple special constants derived from the Balmer series. Only then would it be clear that new physics is required, and it was very unlikely to be a small tweak to existing physics. Bohr succeeded famously, and this was the beginning of a scientific revolution. In 1913, he produced a model with only a single new principle and a single constant already known, and his energy levels were accurate to something like 0.01%, and are still used today, even with a far more accurate theory available. We could say that the Bohr model is perhaps the most successful theory in physics known to be physically incorrect, but forcing a path to the future. Bohr's model begins the era of old quantum theory. Without Bohr's model's match to the Balmer series and the size of the hydrogen atom, quantum mechanics might not have been discovered for decades. More about Bohr at the end of this paper. I'm not giving the exact steps that Bohr gave in his paper. He had to deal with some physics that we don't need to know, and now we know his results. I've reordered the analysis to provide an emphasis on angular momentum that we will need for quantum mechanics. This is consistent with the results of his paper and does not use later material, especially does not use the subsequent de Broglie relation. But if you want, you can read Bohr's paper online. Circular orbits. We will match the electrostatic attraction between the electron and hydrogen nucleus with one proton to the centripetal acceleration required classically to maintain a circular orbit. And we will ignore why the acceleration of the electron does not radiate energy, as there was no valid explanation for this in any event. Most derivations treat the hydrogen nucleus as immobile. We will up-level our derivation slightly by treating the electron as orbiting the center of mass of the atom, and the nucleus as not necessarily being hydrogen. If you are not familiar with center of mass, consider it to be the location of the nucleus and ignore the unfamiliar wording. Let m sub e be the mass of the electron, m sub n be the mass of the nucleus, and m equal m sub e times m sub n divided by their sum be the effective mass of the electron in the orbit, only very slightly smaller than the electron's mass. If you're not familiar with effective mass, consider it to be the mass of the electron and ignore the unfamiliar wording. We will assume a circular orbit around the center of mass, so the Coulomb attraction, opposite charges attract, on the electron due to the nucleus will be a force pointing centrally toward the center of mass, the nucleus. And the acceleration vector of the electron's circular orbit trajectory points centrally toward the center of mass, the nucleus. We can write our formulas in terms of radial scalar, not vector, quantities. By convention, we use outward as the positive quantity and inward as the negative quantity. Coulomb's law of electrostatic force. Force equals K sub E times Q sub 1, Q sub 2 over R squared, which equals minus K sub E times Z times E squared over R squared, where F is the radial force, negative for inward pointing attraction, R is the distance between the orbiting electron and the atom center of mass, E is the elementary electrostatic charge on the electron and hydrogen nucleus and proton in coulombs in SI units. Z is the atomic number of the nucleus, 1 for hydrogen. And K sub E is Coulomb's constant. K sub E equals 1 over 4 pi epsilon 0 when using SI units, where epsilon 0 is the vacuum permittivity of free space. Don't worry about this constant. It's not important to your understanding. Actually, most derivations of the Bohr model use CGS electrostatic units, which are common and natural in electromagnetism. In CGS, K sub E is exactly 1, so we can admit it. But the price for this simplicity is that the elementary charge in CGS units is in electrostatic units, or ESUs, not coulombs, and you're not familiar with how to convert between CGS and SI in electrostatic problems. Eventually, we want to get electron levels in electron volts. It's very common to do the Bohr derivation in CGS units, and then for some students to horribly mess up the final energy calculation and be confused and frustrated. To avoid this, we will keep the K sub E term. If you're looking at a derivation in CGS units, which don't show a K sub E and probably also don't show a Z, there is an easy way to convert those final results to SI units for calculation. You simply replace every instance of E squared in a CGS result with K sub E, Z, E squared as the SI result. We will ignore that moving charges create magnetic fields and moving charges are accelerated by magnetic fields. It should not be entirely okay to ignore this, but it is okay for Bohr's model applied to the hydrogen atom. If the electron is to be in a circular orbit, the Coulomb attractive force must produce the centripetal acceleration exactly to maintain the orbit. So the Coulomb force must equal minus mv squared over r, where v is the tangential velocity or speed. Let's use this to solve for v squared. We get v squared equals k sub e z e squared over m times r. As this stands, any orbital radius is possible. It's continuously variable, just as for gravitational orbits. Given some radius r, the tangential velocity is determined by the formula. We have not yet produced formulas for the electron's energy, but clearly this approach has not yet produced quantized orbits with discrete energy levels that could produce Balmer emission lines. It won't be obvious why, but let's recast the equation in terms of orbital angular momentum. Orbital angular momentum, capital L, equals rmv. So velocity v equals L over m times r. So replacing velocity with L over m times r on the left side, we get quantity L over m times r, quantity squared, equals k sub e z e squared over m times r. Let's solve this for r, treating L as a given. We get r equals L squared over k sub e z e squared m. And we get formulas for v squared of k sub e z e squared over m times r, or if we substitute in the r value, we get quantity k sub e z e squared, quantity squared, over L squared. And we can solve that for v. Bohr's quantized circular orbits. Bohr knew what some of the energy levels for hydrogen had to be in order to produce the Balmer series. So he worked from that. Later in his paper, he showed that the result had a consequence for orbital angular momentum. Angular momentum is important in quantum mechanics, so I'm choosing to give you a different analysis than Bohr's, but consistent with his results and understanding. If orbital angular momentum L took on definite discrete values, that is, was quantized in a particular way for the hydrogen atom, then the circular orbits would take on definite discrete radii, as would tangential velocity and also kinetic energy, potential energy, and total energy, though I have intentionally not yet given these equations. Bohr found that the Balmer series was consistent with constraining the angular momentum L to be L equals n times h bar, and since this depends on an integer n, we will call it L sub n, where n is an integer greater than or equal to 1, and h bar equals h over 2 pi, where h is amazingly Planck's constant from blackbody radiation and from Einstein's photoelectric effect. H bar is called the reduced Planck's constant and occurs everywhere in quantum mechanics. We previously remarked that Planck's constant has units of energy times time, which equals the advanced classical mechanics quantity called action. But it also can be represented as length times momentum, the same units as angular momentum. Bohr radius. Let's solve for the radius now in terms of integer n, which will later be called the principal quantum number, and h bar, and remove angular momentum L from the equation. The radius is no longer arbitrary. It is discrete depending on the quantum number n. So we will give r the subscript n. If we work through the equations for r sub n, we get an equation that r sub n equals a sub 0 times n squared over z, where we call a sub 0 the Bohr radius, which we still use today, even though the Bohr model is definitely physically incorrect. A sub 0 equals h bar squared over m ke e squared. Let's calculate A sub 0 in SI units, meters, even though we have not yet shown that the Bohr model gives the correct energies for hydrogen. I will use the reduced mass of the electron with a single proton nucleus. If we go through the equation for A sub 0 and we substitute in known values for h bar and the mass of the reduced mass of the electron and k sub e, the Coulomb constant, and e squared, and we calculate it out, we get that A sub 0 equals 5.29 by 10 to the minus 11 meters, which is 52.9 picometers, or 0.529 angstroms. We have not checked the energies yet, but Bohr knew that this was the approximate size scale of atoms. Now I'm showing a diagram of the Bohr orbits for hydrogen, showing the n equals 1, n equals 2, and n equals 3 orbits, which have radius A0, 4A0, and 9A0. Bohr energy levels and the fine structure constant. Let's develop the energy levels as a function of quantum number n. The total energy is the sum of the kinetic energy T, capital T, plus the potential energy, capital V. T will be positive and V and E will be negative for the circular orbit bound states. You might not remember or be familiar with the electrostatic potential energy. E sub n equals kinetic energy 1/2 mv squared minus plus the potential energy, which will be minus k sub e z e squared over r sub n. If we plug in values for v sub n and r sub n and do the math, we notice that the kinetic energy term is equal to half the magnitude of the potential energy term. This is a well-known result in advanced classical mechanics called the Virial Theorem for the 1 over r potential. Energy level E sub n equals minus m over 2 times quantity k sub e z e squared, quantity squared, over angular momentum squared. Let's substitute that angular momentum, L sub n, equals n times h bar. Let's multiply the numerator and denominator by the speed of light squared and rearrange the equation. What we get is that the energy E sub n equals a product of 3 terms: minus mc squared over 2, alpha squared, and z squared over n squared, where alpha is called the fine structure constant. Alpha equals k sub e e squared over h bar c. mc squared is the rest mass energy of the effective mass of the electron. Let's calculate the fine structure constant alpha numerically and its units from SI values. If we multiply all the known factors together, we get that alpha equals 0.007297, or 1 over 137.04, and there are no units. All the units cancel. The fine structure constant alpha has no units. It has the same value no matter what system of units we choose. It's a constant of the universe. It would have the same numerical value for an alien civilization no matter their system of units. As far as we could tell, the value of the fine structure constant has not changed since the first galaxies in our observable universe started shining. Physicists remember the fine structure constant as being about 1 over 137. We can think of the fine structure constant as the strength of the electromagnetic force relative to the strong nuclear force. That is, it's 137 times weaker. mc squared is the rest mass energy of the reduced mass of the electron, and it is almost 511,000 electron volts, and it would be 511,000 electron volts if we use the electron's unreduced mass. If we combine the rest mass energy with the square of the fine structure constant, this gives us two important energy values. The first is called the Hartree, which is written as HA, and it is the rest mass of the electron times alpha squared, and it is 27.2 electron volts. The other value is called a Rydberg, written RY, and it is 1/2 of that, 13.6 electron volts. Bohr's physically impossible circular orbits, plus his result that the orbital angular momentum is quantized in units of h-bar, gives us the following energy levels for a hydrogen atom or a hydrogen-like ion. The nth energy level is minus 13.6 electron volts times the atomic number z squared divided by n squared. The hydrogen atom's ground state has n equals 1, and its energy is minus 13.6 electron volts, where zero energy is infinite separation between the electron and the proton, and negative energies correspond to bound states. Now I'm showing a graph of the energy, the potential energy, the kinetic energy, and the total energy, and energy as the vertical axis, and the horizontal axis is the radius of the circular orbit in units of A0. So for n equals 1, we have minus 13.6 electron volts as the binding energy or the total energy. For n equals 2, we have minus 3.4 electron volts, and the radius has gone from 1 Bohr radius to 4 Bohr radii. For n equals 3, the binding energy is minus 1.51 electron volts, and the radius is 9 Bohr radii. The hydrogen-Balmer series photon energies are the result of a transition from a level m greater than 2 to the level n equals 2. And the energy difference, the Balmer energy, is 13.6 electron volts times 1 over 2 squared minus 1 over m squared, where m is greater than 2. This is the energy formula that Bohr needed to produce to match the Balmer series. He knew he needed to do that. Bohr worked from this formula to get the radii he needed. He then found that the orbital angular momentum was quantized in units of h-bar. We took the approach of assuming that quantized orbital angular momentum, and we were able to get Bohr's correct energy formula for the Balmer series. Here I'm showing the Balmer lines, their energies, and how they relate to the hydrogen atom energy levels. And I'm also showing their wavelengths in nanometers and their color, the color that we see them. The Balmer alpha line, which is also called the hydrogen alpha or H-alpha line, is 1.89 electron volts. It's 656 nanometers, and we see it as red. We also see the Balmer beta, gamma, and delta emission lines. We see them as colors aqua, blue, and violet. We were able to create a nuclear model of the hydrogen atom with unphysical circular orbits, a single new principle, quantized orbital angular momentum, and an existing experimentally determined constant, the reduced Planck's constant, h-bar, and produce the Balmer series. Had no one succeeded in developing and publishing such a model, knowing that it was physically incorrect and subject to professional ridicule, we might have waited a long time for anyone to figure out the quantum world. Bohr's model, which began old quantum theory, is wrong, but it forcefully requires that new physics be developed and that it reproduces Bohr's results. The de Broglie wavelength of the electron. Some introductory quantum mechanics books will explain the Bohr model by desire to find orbits where the circumference of the orbit exactly matches an integer multiple of the wavelength of the electron, treated as a wave. But de Broglie or de Broglie's hypothesis that the wavelength of a particle with mass is lambda over Planck's constant h divided by momentum, mass times velocity, that wavelength formula would not be published until 1924, 11 years after Bohr's paper. Nevertheless, let's show that Bohr's hypothesis that angular momentum L equals n over h bar does correspond to an integer number of de Broglie electron wavelengths in the circumference of the orbit, even though this also is physically impossible. Angular momentum L sub n equals n times h bar equals n times h over 2 pi, and that angular momentum equals mass times the velocity v sub n times the radius r sub n. If we rearrange the equation, we can get 2 pi r sub n on the left side, and we end up on the right side with n times h over m times v sub n. If we apply the de Broglie formula, we would get n times the wavelength lambda sub n. So on the left side we have the circumference 2 pi r sub n. On the right side we have an integer times the de Broglie wavelength, just as we sought to prove. Some learners find that these standing waves help them make sense of the Bohr orbits in a way that the equations don't. I'm showing a drawing of the standing waves for values n equals 1, 2, and 3. However, please realize that these orbits don't really exist. So here's the graph where this purple curve is showing n equals 1, the black curve is showing n equals 2, and the red curve is showing n equals 3, each having an integral number of de Broglie wavelengths in their orbit. The de Broglie wavelength changes from n equals 1 to n equals 2 to n equals 3, but each has an integral number of that wavelength in its orbit. Heisenberg Uncertainty Principle. Heisenberg's Uncertainty Principle, published in 1927, states that the uncertainty in a particle's position in some direction times the uncertainty in its momentum in that direction will always be larger than or equal to the specific minimum value h bar over 2, no matter the system, the state, or the measurements used. Let's check this using our results from the Bohr model. In this paper, we don't want to deal with the details of the actual definition of the uncertainties, so we'll use a reasonable approximation. For the uncertainty in position, we'll use the radius, r sub n. For the uncertainty in momentum in the x direction, we'll use mass times the velocity, v sub n. When we take the product of these two uncertainties and we work through the math, we end up getting that the product of the uncertainty in x with the uncertainty in momentum in x equals h bar times n. And this is always greater than or equal to h bar. So the product of these uncertainties is larger than or equal to h bar over 2. However, we only used approximate formulas for the uncertainties. To do this correctly, we would have to use quantum mechanics. It is true in quantum mechanics, but we're not going to do that work in this paper. Note that this product was independent of the atomic number z. Now you might recognize that this follows from the angular momentum quantization. Let's use the equations for r and v that still had L in the equations. Here I'm showing the equation for r that has L still in it, and the equation for momentum mv that still has L in it. And when we multiply them together, we get that the product equals the angular momentum L, and that is the quantized value n times h bar, and that is always greater than or equal to h bar. Planck's constant, the quantum. Planck's black body radiation work in 1901 identified Planck's constant h as the quantum of action, energy times time, for the blackbody cavity radiation interactions with the hot walls of the cavity. Existing power spectrum data determined the value of Planck's constant. Einstein's photoelectric paper in 1905 identified that light acts as though quantized in energy when liberating electrons from a clean metal surface in a vacuum. The amount of energy in a particle of light, later named a photon, depends on the frequency or wavelength of the light, and the constant of proportionality is Planck's constant. So E equals h nu, where nu is frequency, or equals hf, where f is frequency, or equals hc over lambda, where lambda is the wavelength. The Bohr model of 1913 identified the reduced Planck's constant, h bar equals h over 2 pi, as the quantum of orbital angular momentum for the hydrogen atom. Nothing in Planck's blackbody radiation work jumps out and screams orbital angular momentum, but somehow these both signal that new physics is required, and this new physics, quantum mechanics, uses Planck's constant in determining results, and as its scale for when results differ from classical mechanics and classical electromagnetism. Beyond the Bohr model. New, modern quantum mechanics. It would not be Bohr who developed the physics that we now call quantum mechanics. It was Heisenberg, Schrödinger, Born, Pauli, and Dirac. However, Bohr was instrumental in birthing quantum mechanics. He welcomed students, postdocs, fellow physicists to his lab to discuss the state of quantum theory. He traveled to other physicists' cities and labs and talked with them. He asked essential questions. Einstein publicly doubted quantum mechanics multiple times with insightful, seemingly fatal points. It was Bohr thinking deeply who successfully explained how to think about the new physics to refute Einstein's points. Bohr's contribution was immense. Bohr won the Nobel Prize in 1922, a few years before correct quantum mechanics was discovered. Even though his model was definitely wrong, but definitely useful. How does Bohr's model compare with quantum mechanics' explanation of the hydrogen atom? Bohr's energy levels for hydrogen are accurate to 1/100%, and that's amazing. There are no orbits. The electron's position is described as a very specific, diffuse, three-dimensional cloud of probability specific to the quantum numbers of the state that the electron is in. Bohr's orbits were in 2 dimensions. Matter and atoms are 3-dimensional. Anytime you're tempted to draw or visualize a 2-dimensional orbit for a 3-dimensional atom, stop. This is an incomplete model of real atoms. There is irreducible uncertainty in how well we can simultaneously know or measure the position and momentum of the electron. It is not in an orbit. I hate that we still diagram atoms for elementary and high school students as orbits. We're handicapping those students with an incorrect mental image that they will never get out of their brains. Though there are no orbits, there is orbital angular momentum, and it is quantized in units of h bar. However, the actual ground state has 0 orbital angular momentum, unlike the Bohr model. How can there be a definite orbital angular momentum, but not circular orbits nor elliptical orbits? The following diagram shows many momentum vectors originating from 8 positions to the right of the nucleus. all of these momentum vectors, which point in many different directions, they all have the same identical value of orbital angular momentum. We can have a constant orbital angular momentum without circular or elliptical orbits, or even trajectories as functions of time. The Bohr model doesn't extend to the following cases, but quantum mechanics does, though it is complicated. Explaining excited state, half-life, and natural line width. Atoms with more than one electron. Placing atoms in an electric field or magnetic field. Molecules, bonds, bond lengths, bond energies, vibrations, rotations. Crystals, solids, semiconductor bands, and electronics. Stimulated emission and lasers. An intrinsic spin angular momentum of the electron was unknown before 1922 to 1928. Bohr's model is non-relativistic. It assumes that the electron is traveling substantially less than the speed of light. Relativistic corrections are required when the ground state energy becomes comparable to the electron's rest mass energy. So for heavy atoms, core electrons, where Z becomes comparable to 1 over the fine structure constant. The factor of the relativistic energy corrections is on the order of alpha squared, so about 0.005% correction. It was pretty fortunate that relativistic corrections would be so small, or it would have been even harder to discover quantum mechanics. I hope there were no errors in this paper, and that you could follow this, and it was worth your time.